বুঝতে পারছে না, আমি বলি ভিজুয়ালাইজ করতে পারছি না। ম্যাথমেটিক্স বোঝা আর ম্যাথমেটিক্স ভিজুয়ালাইজ করাটা এক জিনিস নয়। আমরা মহাকাশে যখন রকেট পাঠাই, আমার যা ধারণা বলছি, তখন যিনি তার হিসাবগুলো করেন, কিন্তু হিসাবটা তিনি ভিজুয়ালাইজ করেন। সেই হিসেবে বা সেই হিসেবেই রকেটের প্ল্যানিং করতে হয়, রকেটের ফোর্স ক্যালকুলেট করতে হয়। শুধু ক্যালকুলেট নয়, ক্যালকুলেশনের পরে যেটাকে ভিজুয়ালাইজ করতে হয়। এই জায়গায় একটা ল্যাক, অভাব থেকে যাচ্ছে দীর্ঘ যুগে যুগে। সেই জন্যই বোধ হয় ম্যাথমেটিক্সের স্টুডেন্ট কমে যাচ্ছে, ফিজিক্সের স্টুডেন্ট কমে যাচ্ছে। এই ফিজিক্সের, আমি কালনা কলেজের ইয়েতেই বলছি, ফিজিক্সে ভর্তি হওয়ার জন্য একটা সময় ছিল বিরাট কম্পিটিশন। ফিজিক্সে বর্তমানে ফিজিক্স ভালো ভালো ছেলে বলছে না ফিজিক্স নেব না। আসলে ফিজিক্সের ভিত্তিটা নয়, ভিত্তিটা কিন্তু দা ম্যাথমেটিক্সে। ব্লেম দিয়ে লাভ নাই। বেস লেভেলে, স্কুল লেভেলে ম্যাথমেটিক্সটা ছাত্রদের মাথায় ঢোকানোর ক্ষেত্রে, অর্থাৎ ম্যাথমেটিক্সটা আন্ডারস্ট্যান্ডিং লেভেলে যাওয়া বা ভিজুয়ালাইজ করা। কারণ ফিজিক্সে ম্যাথমেটিক্সটা করা মানে একটা জিনিসকে, কনসেপ্টকে ভিজুয়ালাইজ করা। এই জায়গায় অনেক ঘাটতি থেকে যায়। এটা আমি আমার ব্যক্তিগত অভিজ্ঞতা থেকে বললাম, যে আমি যা দেখেছি, যা বুঝেছি, সেই থেকেই বললাম। তর্ক বিতর্কের মধ্যে আমি যাচ্ছি না, কারণ আমি প্রথমে স্বীকার করেছি ম্যাথমেটিক্সের দৌড় আমার এই শেষ পর্যন্ত। এইটুকু বলে কালনা কলেজের আইকিউএসি এবং সামগ্রিকভাবে কালনা কলেজে যারা বর্তমান নবপ্রজন্মের অধ্যাপক রয়েছেন, আমি বছরখানেক হলো এই জীবিতে আছি, তাদের আমি খুব ঘন ঘনই আসি। অনেক কিছু বাইরে থেকে শুনতাম, কিন্তু এই নতুন প্রজন্মের যে টিচিং স্টাফ কালনা কলেজে দেখছি, সত্যি আমি এদেরকে খুব শ্রদ্ধা করি, রেসপেক্ট করি। কারণ এরা ভীষণ এনার্জেটিক, এরা কিছু করতে চাইছে ছাত্রদের জন্য। ছাত্রদের জন্য করতে চাওয়া মানে সমাজের জন্য করতে চাওয়া, সমাজের জন্য করতে চাওয়া মানে দেশের জন্য করতে চাওয়া। তাদের এই এফোর্টকে আমি আরেকবার পুনিশ করছি, সাবিত করছি। কালনা কলেজকে, ম্যাথমেটিক্স ডিপার্টমেন্টকে আমার থ্যাঙ্কস জানাচ্ছি। ধন্যবাদ।
আমাদের সামনে আজ একজন বিশেষ ব্যক্তি উপস্থিত আছে। তার নাম হচ্ছে চন্দ্র চ্যাটার্জি। তিনি বর্ধমান ইউনিভার্সিটির এমিনেন্ট প্রফেসর। ইনার পাণ্ডিত্য এতটাই যে নাম শুনেই সবাই জানে। এমন ব্যাপার যে বর্ধমান ইউনিভার্সিটির ম্যাথমেটিক্স ডিপার্টমেন্টে যদি সর্বকালের সেরাদের লিস্ট করা হয়, ওনার নাম উপরের দিকে থাকে। একটা ছোট্ট ইনসিডেন্ট আমি বলি। আমরা 2006-এ একটা ওরিয়েন্টেশন প্রোগ্রাম করেছিলাম, যেখানে ফিজিক্স ডিপার্টমেন্টের পাঠদাও ছিলেন। উনি একটা ম্যাথমেটিক্সের টপ দিয়েছিলেন, নাম্বার 3। ওরিয়েন্টেশন প্রোগ্রামে হেটেরোজিনিয়াস সাবজেক্টের টিচাররা থাকে, উনি টপটা দিয়েছিলেন। পাশে একজন আর্টসের টিচার ছিলেন, তিনি আমাকে বললেন খুব ভালো লাগলো টপটা। সবকিছু বুঝিনি, যেটা বুঝলাম উনি হচ্ছে মহান পণ্ডিত। এটা শুনে বোঝা যাচ্ছে ওনার টপ, উনি যা বলবেন বোঝা না গেলেও যে কোনো লোক ভাববে খুব সুন্দর লাগছে। অনেকটা এরকম যে আননোন ভাষায় যখন আমরা কোনো গান শুনি, গানের কথা একটা বোঝা যায়।
তাই করে দেবে, তাই ঠিক আছে, আমি দেখে তোমাকে আর 10 মিনিট পরে বলে দিচ্ছি, ঠিক আছে? হ্যাঁ ঠিক আছে। বলে দিচ্ছি, ঠিক আছে, বলে দিচ্ছি।
ये तो बोल আসছে না এটা দাও না, কি বলে ওটা দিচ্ছ না তুমি? এটা আছে তো, দাও। আমি লাগাবো কি স্ট্যান্ড নাই তো, কোনটা আছে ওটা? ওটা তো হাতে ধরে বসে, হ্যাঁ বসে বসে বলি, ওটা তো অসুবিধা গেছে, বসে বলি ওটা দিলি তো বেটার। এইখানটা দিন, এইখানটা বসে
সাথে পড়ে গেলে যা হয়, আমাদেরও পরীক্ষা চলছে, হয়েছে কি হয়েছে?
এটা দুটো একটু
হ্যাঁ এই
ফুল স্ক্রিন করতে স্পিকারও তো শোনা যাবে
এইখানে বলতে সুন্দর হবে। চার্জার আছে স্ক্রিনটা বড় করে যাবে
এটাই ম্যাক্সিমাম
স্ক্রিনটা বড় হচ্ছে না।
এটাই ম্যাক্সিমাম স্যার ফুল স্ক্রিন হচ্ছে ফুল স্ক্রিন এটাই ফুল স্ক্রিন আছে
স্পিকারকে দেখতে পাওয়া যাবে না আবার।
স্পিকারকে দেখতে পাওয়া
দরকার নেই অসুবিধা নেই
ওই করে দেখতে পারে
ঠিক আছে জুম কর
না নিচে কেটে যাবে নিচে কেটে যাচ্ছে
ও স্পিকার উপরে এসে গেছে। হ্যাঁ বড় করে দাও।
কেটে যাচ্ছে
লেখাটা বড় সমস্যা। ঠিক আছে লেখা বড় সমস্যা।
এটাকে মিনিমাইজ করে না ওইটা ঠিক ছিল আগেরটা ঠিক ছিল ল্যান্ডস্কেপ মোডে এটা ঠিক আছে এটা আমি ছোট করে দিচ্ছি এই আইকনটা সরিয়ে দিচ্ছি ওটা যাবে না এটা মিনিমাম স্পটলাইট দেওয়া ওটা থাকবে ওইটুকু থাকবে
Okay, so I thank Kalna College for inviting me to give such talk, and Abhishek, friend, so principal for arranging all this. Very happy to be here. So I'm going to, let's not extend any other things, so just get back to the lecture. So I'm going to talk about differentiable manifolds and groups. So yeah, so let me straight go and define Lie groups in the most formal way, and then we'll see. In the beginning, I'm not expecting that you will follow this formal definition, but then my job is to explain all the terms in the definition, and that's the job. But we'll also say a few words about why Lie group is important. Okay, so let's define okay, so I'm going to write certain terms. Some of them are going to be known to the students in mathematics, and this lecture is meant for mathematics students, I guess. So G is a group. That means it is a set with some binary operation which satisfies a bunch of properties. Okay? And then G is a differentiable manifold. This term, most of the students may not know. I'm going to explain. Then G is said to be a Lie group. Here, the group structure and the manifold structure are compatible. They talk to each other. What does that mean? That means the map, the group multiplication xy going to x dot y, and the inversion x going to inverse. These are both smooth map. I'm going to explain this. Okay. So I'm going to explain it in the most general way without trimming any generalities, these terms. That's going to be the aim of this talk. And then if there is some time left, we'll go about describing some more properties of these. So if you don't understand these terms, don't be disappointed, okay? Because I'm going to soon tell you what these terms are. Okay? Now let's see some let's keep some examples in mind. So I take the real number with addition. Okay, this is an example of a Lie group. Okay. Then I have f r to the power n, again with coordinate wise addition. This is also another example of a Lie group. We all know that these two are abelian. Okay. Now let's take GLNR with multiplication, matrix multiplication. We all know that this is a group. This is an example, yet another example of a group. And we know that this GLNR is non-abelian when n is strictly greater than 1. Okay? If GL1R is just simply R star, non-zero real numbers multiplication. So these are examples of Lie groups. Okay, these two are abelian, and this is non-abelian. Okay, it's good to keep some examples before we proceed the generality. So these R is a differentiable manifold. Soon we are going to see why they are. Rn is also a differentiable manifold, and GLN and R also a differentiable. And addition, inversion is just taking negative. And here also inversion is taking negative. They're all smooth maps. Multiplication is also smooth maps. We have some, although we don't know differential manifold, we know that this xy from R across R to R, xy equal to x plus y, it's a smooth map. It's a C infinity map, infinitely differentiable, and so on. And similarly, x equal to minus x is also infinitely differentiable. Okay, in the sense that we know some Rn calculus, right? Similarly, this GLN is also a Lie group. Matrix multiplication is smooth, and matrix inversion is also smooth. We're going to see why. Because multiplication, we all know that it's a smooth map because GLN is an open subset of USP. Here it is okay. I will just remove it. Can you hear?
Okay, this is better because I'm hearing my own noise, so it's disturbing. Yeah. So this is not better.
So inversion of a matrix can be represented in terms of the matrix. You know, like there is called adjuvant of a matrix and so on. So those are entries. Inversion, the formula for inverse can be expressed in terms of the coefficient of a matrix, right? That we all know. This is why inversion is smooth. Okay. But let us now say a few words about why Lie groups are important. Why the groups are important. This is because there are several reasons. So Lie groups was invented by a mathematician called Sophus Lie, and he wanted to have some kind of theory for differential equation analogous to what we see for fields. So the Galois theory to fields is the relation of Galois theory to fields is has the same. I mean, you have to develop a same kind of theory for differential equation, and can you have a group which controls properties of differential equation? That was his name. That's why he invented groups. These used to be called as continuous groups. Now, my point of view is more that of involving geometry. So this was a program, started by Felix Klein. Said that you want to understand geometry of space, you want to understand the symmetry of space. Okay? So this is the famous Erlangen program of Felix Klein. So this is why Lie group is important. If you want to understand a space, you understand its symmetry. Symmetries contain a lot of information about space. Also, let me just say a few words. Don't be disappointed if you don't understand this. So if I take M to be a Riemannian manifold, so as I was coming with Professor Devashish Babu Sahib আসছিলাম তখন উনি বললেন যে Riemannian manifolds are objects very important to relate. So let me give this example of Riemannian manifold. So Riemannian manifold are manifolds with the concept of distance, naturally coming from some metric on, so manifold from equal to something called tangent space, okay, and every tangent space is a metric in a smooth way. This gives me a Riemannian equation. Don't be disappointed if you don't understand all this technical jargon. But Riemannian manifold can talk of distance. This is a, you can do geometry on that space. So manifolds, so topological space are spaces where you can talk of continuous functions. Manifolds are spaces on which general spaces, like we have seen continuous functions on Rn and so on, right? But we want to go beyond that. Okay, so this is why we have empty spaces and topological spaces. And topological spaces are the spaces where you can do talk of continuous functions. And manifolds are spaces where you can talk of differentiable functions. And Riemannian manifolds are those spaces where you can do Euclidean geometry, like you see Euclidean geometry on R square and an R square. You can do geometry. So if I take a Riemannian manifold, then something called an isometric group. That means the group of all transformation of these spaces which preserves distances. This is called isometric group. All differentiable C infinity map from M to M. I mean by C infinity map which preserves this distance are called isometric. They form a group, and this group has a Lie group structure. This is a very deep theorem due to Myers and Steenrod. Okay, so this is a theorem. This is a non-trivial fact. They prove that this group, if I take any Riemannian manifold, then the group of isometry has a Lie group structure. Okay, it's a finite dimensional Lie group structure. That's somewhat very strange. Then, so this Lie group gives a lot of information about M if I choose a particular kind of Riemannian manifold, and they are called symmetric spaces. Okay, so symmetric spaces are in fact constructed from their isometric groups. Now let me take another example. Take M to be a compact complex manifold. Then there is something called holomorphic maps between complex manifolds, and the biholomorphic maps from M to M, they also form a group if the space is compact. This is also a very important result proved in the books of Kobayashi and so on. So, for example, if I take, we have seen this C hat. If you have done a little bit of complex analysis, which is also there in BSc courses now, C union infinity. It's a sphere on which we can give a complex structure. Then we know out of C hat, these are Mobius transformations. Okay, that means this out of C hat is SL to C mod plus minus identity. This group is isomorphic to this. So you see, here is an example of a very special compact complex manifold called C hat. This is the same as unit sphere. You can give a complex structure on that. Then out of C hat, the automorphism is by Mobius transformation, which is SL to C by plus minus identity. This is a complex Lie group. This is just to give an idea of why Lie group is important. Okay, so these are the reasons. I am just giving examples of spaces which are controlled by their isometric groups. The group of symmetry. So these are the spaces. This Lie group says a lot about the spaces. So this is why Lie group is important. Lie group is important in almost every important branch of mathematics, be it number theory, be it geometry or algebraic geometry or several other topics. They are all is a very important object. And there are several Indian mathematicians who have made fundamental contributions in Lie theory. Starting with you have seen the name of Srinivasa Ramanujan, who is a famous number theorist, but there is an equally important mathematician who is not so well known. His name is Harishchandra. So Harishchandra is an Indian mathematician. He was initially a physicist. He had made an immense contribution to the theory of Lie groups, especially on there is a subject called representation theory of Lie groups. He is thought to be the god of that subject. Okay, so this year they commemorated certain birth year of Harishchandra, maybe 100th birth year of Harishchandra in an institute called Harishchandra Research Institute in Allahabad. Okay, so he was initially a student of Homi Bhabha, the founder of Indian nuclear program, and then he became a student of Paul Dirac. Then he quit mathematics. He started his career with physics. Then he became a mathematician, and mathematician to unbelievable that from a career of physics he went on to become one of the greatest mathematicians in India as well. And he is one of the major leads. So there are other mathematicians in India also who made major contributions in this. Okay, so let me now try to explain all these terminologies. We all know what is a group, abstract group. We are not going to that, but let me just give. So, what is a differential manifold? So, to do this, first let us understand a topological space. Okay. So, what is a topological space? So, X is a set, and T is a collection of subsets such that satisfying a bunch of property such that the empty set and X is in T, and T is closed under arbitrary union, and T is closed under any finite intersection. That means I have a set. Let's take X to be non-empty, because there's nothing to do. You cannot do anything with empty sets. And I take the collection of subsets satisfying this property. These two sets are there. The empty set is there, and the whole space set is there in that collection. And if I take any collection of subsets that are there in T, their union should be in T. And if I take any finite number of subsets of X which are in T, their intersection should be in T. Okay, so this gives rise to something called a topology. Okay? And X becomes a topological space with this topology. So, what are examples of topology? So, for example, I can simply take T to be phi and x, then this satisfies all this property, because if I just start with a non-empty set x and I take these two sets, this has this property that T is closed under. There are only two elements, so there is no point checking all this. So it is immediate that T gives a topology. This is the worst topology on X. Okay, so this is the uninteresting topology. Okay, so let's take another topology of, and let's go to the other extreme. So let T set of all subsets. Set of all subsets. So given a set, I have taken only two subsets, namely, given a set, I have this phi and x. Okay, this is called the indiscrete topology. And here, set of all subsets also satisfies all this property. Empty set is there, whole set is there, and if T is closed under arbitrary union, because I have taken all subsets, T is closed under finite intersection, in fact all intersection. So T gives me a topology. Okay, so this is called the discrete topology. So by the way, elements of T, so elements of T which are subsets of X are called open sets. Okay. So given any set, I can have two topologies, namely the discrete topology and the indiscrete topology. These are most uninteresting topologies because we completely understand what they are. Now it's the topology in between, they are more complicated, and that's how they become interesting. Okay. So we all know what a metric space is. So this be a metric space. That means metric space is taught in BSc these days. When I was a student, it was not taught, but I think they are taught in BSc these days. Metric spaces. So I can form a topology from this metric space. How do I form? So let's define open balls. So let's take a point X, and so X is a point in X, and R is a positive real number. Okay. So let's define this to be open balls. That means I'm considering all y in X, such that D of xy is strictly less than R. Okay. So these are open balls. Now I declare, so let us call a set to be open, a set U of X to be open if it is union of open balls. Okay. So you can check. This is an nice exercise to check. So this is an exercise for you to check that. So this gives, so T be the union of open sets in the above sense, then T gives topology on X. That we all know. Right? Okay, to define manifold, I need topology, I need something called the concept of Hausdorffness. Okay, that means, so let us define definition. So xt be topological space this is called Hausdorff. This is called Hausdorff space if any 2 points can be separated by open sets. Okay, let me draw a picture. So here is my X. I have alpha, beta 2 points here. If I have 2 open sets, one containing alpha, the other containing beta, such that they are disjoint. That means 2 points can be separated by open sets. Any 2 points, any 2 pair of points. If any pair of points alpha beta with alpha not equal to beta, there is u p u containing alpha, b containing beta, such that u intersection b. That means that is joint. Okay. Right? So, what are examples of a Hausdorff topological space? Any metric space is an example of a Hausdorff topology. That is easy. So metric spaces give topology. That gives an example with respect to that topology. The metric space becomes a Hausdorff topology. That is easy because example, any metric space XD is Hausdorff. So that is easy because you take any 2 point alpha beta. So there is a distance, right? If alpha is not equal to beta, there is a positive distance. You just take the half, and suppose the distance is r. You take a ball with radius say less than half of r, and here half of r, they will not disjoint. Okay, so you take something, the distance is half. This distance is half of r. This is just the same intuition applies that you apply for your Euclidean geometry. Half of r, and you take something smaller than half, and that will give a disjoint ball. And these balls are by definition open sets, so they are. So this gives you a Hausdorff example of Hausdorff. So there are. So and you can look up more examples of Hausdorff topological space because of this fact, because you know that my Rn has the usual metric d, that is d of x1, xn, y1, yn is simply square root of x1 minus y1 square, xn minus yn square. This gives you a metric that we all know. This is the usual metric in Rn. And so this is an example, Rnd is an example of a Hausdorff metric space because we have just now seen the general metric space is already. Okay. All right, now I need the concept of a second countable topological space. Okay. So let me before that, let me give an example of a non-Hausdorff topological space. So Hausdorff topological space are in abundance. So it is difficult to get a non-Hausdorff topology. Okay? So I take a set which has more than 2 points and get the indiscrete topology. Okay? So one should, Hausdorff topological spaces are easy to, in fact, most of the spaces that you see are Hausdorff. So example of a non-Hausdorff one example immediately comes from this indiscrete topology. So let's take X and suppose X has more than 2 points. Then the indiscrete topology is non-Hausdorff. And that is immediately visible because I have to separate 2 points from open sets, but I don't have much open sets. The open sets are only empty set arrays, so you cannot separate. If anything, if I have non-empty open set, that contains X. Okay, so this is an immediate example of a non-Hausdorff space, topological space. So non-Hausdorff spaces exist, and one should keep in mind that they also exist. Although it is quite, they're not. You cannot find. You have to work hard to find examples as opposed to examples of Hausdorff spaces. Now, I need the concept of second counter. After this topological preliminaries, we'll go and do some basic Rn to Rn calculus. Okay? So for this, I need the concept of base for a topological space. So X, T, be a topological base space, and B be a subset of T. Then B is called a base for a topological space if every open set can be written as union of sets from okay. So T is a collection of subsets which gives me the topology, and T elements of T are called open sets. A smaller collection is called a base. A smaller collection from T is called a base if every open set can be written as union of elements from T. We have seen already the way we have defined the topology on metric space. We have seen that open balls in a metric space gives me a base. Okay. So example. XD, a metric space. Then we have defined the topology by defining a set to be open if it is union of open balls. So by very definition, this B, which is a collection of balls, collection open balls. This is a base. This is a base for topology on. Okay. For example, if I take real numbers, the set of real numbers, then the open sets are union of open intervals. Open intervals form a base. Okay. Open intervals are precisely the open balls in real numbers. Okay. So if x is equal to r, then open intervals, collection of open intervals gives us base for the topology on R. Okay, so now definition. Topological space is called topological space XD is called second countable if there exists a base which is countable. That means the cardinality is that of the set of integers. We know what a set is, we know what is the meaning of a countable set, right? We all know what that it means. So for example, let's give some examples of second countable spaces. This topology of R is an example of a second countable space. And why? I can consider open intervals with rational endpoints. So I consider B to be open intervals alpha beta, where alpha beta is in Q. This is of course a countable set, and this is an easy exercise to show that any set is a union of any open interval is a union of open intervals with rational endpoints. Okay. Similarly, Rn with usual distance is also an example of a second countable space. Okay. Now one can characterize the second countable metric spaces. Okay. Since you have seen metric spaces, so let XD be a metric space. This metric space under the usual metric topology is second countable if and only if it is separable. That means it contains a countable dense subset. So XD is second countable if and only it is separable. Okay. So this is the easy fact to check. First of all, if XD is second countable, that means it has a countable base. I choose that base and pick up points from the sets in the base. That gives me a countable dense set. Okay. That's easy to see. Okay. So this is why it is separable. Now, if it is separable, what is the definition of a separable metric space? A metric space is separable if and only if it has a countable dense set, right? Now I choose the countable del set and I choose balls with rational radius. Okay, that gives me a countable set, and that's going to be a countable. Okay, so to prove that, I gave you orally the proof of the fact that a matrix space is second countable if and only if it is separable. Okay, so we have enough examples of second countable space provided you check such properties. There are non-separable spaces. Okay. Also, I mean, you can take a uncountable family of circle and you just join the circle at one point. Okay. So I take the picture is not correct because what is this? So now another example. What is it? Oh, Google Swaraj? Check it out.
শুরু হয়ে গেছে পেজে চলে যাও ঠিক আছে
Right. Okay, XD is second countable if and only if it is separable if XD is a matrix space that we have seen. So we have seen enough examples of second countable topological spaces. So one should also give an example of a non-second countable space. So if I take, so the point is, if I have in a topological space, you have a uncountable many pairwise disjoint open sets, that cannot be second. Okay, that's because every base, every open set can be written as union of bases. So if I have a topological space which has uncountable many open sets which are pairwise disjoint, this cannot be a second countable space. So, for example, if I take an uncountable set and I put the discrete topology, it's not going to be second. Okay. So these are disconnected example. If you want to take a connected example, here is an example. You take an uncountable family of circles, okay, and join them at a single point. Okay. This topological space. So this topological, it's like a. So basically, I am taking another circle. The picture should not be like this because this cannot be embeddable inside Rn. It's like this. I'm taking another circle, then another circle, joining. So and I'm doing it with uncountable unicycle. This cannot be a second countable topological space because I can find disjoint uncountable family of open subsets. For example, if I remove this point where I'm joining, that gives me open sets. Okay, and these open sets are disjoint. So this cannot be. This is an example of a connected set which is not second countable. Okay. So one should have lots of examples in mathematics. So you should always keep examples in mind whenever you have theorems or counter example to a theorem or whatever. So here is, I have given you example of second countable space. I have given you examples of spaces which are not second countable, and examples of not disconnected non-second countable space are easy to construct because I can take the discrete topology on an uncountable set. But I can also using this one point union of uncountable unit circle if I take. Then if I put the correct topology, which is called the quotient topology, you have to know a little bit, it's a little sophisticated example. I take the disjoint union of such circle and I take one point union there. So you have to know a little bit of topology, but there are spaces I can construct like this. And these spaces have the property that I have, this spaces gives me an uncountable disjoint open sets. So this space cannot be a second countable. So this is a nice game actually to find examples of non-countable non-second. Okay, now let me switch my gear and I'm going to recall some Rn to Rn calculus. So, okay, so this is taught in this BSc courses these days.
Actually, R2 to R3 calculus.
R2 to R3. So if you know R2 to R3 or R3 to R2, it is sort of similar. It is just that is enough for us to know. So let us understand what do we mean by differentiable. What are they? Yes. So I understand. So I know, or what is the derivative? What is the meaning of a derivative? What is the meaning of the derivative at a point A in R? Derivative of what are they? Okay. We know what they are. You all know. We all know F A F, and what is the meaning of derivative of F? Right? You all know this, right? When both M and N is equal to 1, you all know what they are. Right. You all know what they are. And I'm going to tell you some kind of motivation or how to generalize this concept to get the right definition of a derivative of a map from Rn to R. Okay, so let us recall the derivative. So A is in R, F is as usual. So what is the derivative? This is limit f of A plus H minus f of A divided by H tends to 0 if this exists. Then we say f is differentiable at A, right? That is what you know. But then there's a problem if I replace Rn and Rm. I cannot just do this thing here. Why I cannot do? Because here, if the domain is in Rn, then A is in Rn, H is in Rn, the upper part is okay, I can evaluate the function, everything makes sense. But dividing by a vector, that doesn't make sense. Right? I cannot divide a vector by a vector. I can divide it by scale. Okay? I cannot divide it by a vector. Okay, so let's reformulate this definition so that I can adapt to the situation in Rm to R. So this means this limit exists is equivalent to saying that there. So this is equivalent. The above is equivalent to saying that there is a C such that limit of. I'm just reformulating the definition that I know so that I can adapt. Okay. So let us rewrite this again. There is a C such that limit of f of a plus h minus f of a minus ch divided by h is equal to 0. Right? I can do that. I can even put a mod here. Right? So now, what are the linear transformations from R to R? Linear transformations from R to R is by multiplication. So I'll make this definition a little sophisticated. I will not say there is a C, but I'll say that there is a linear map. Let's say L from R to R linear map. Such that limit of f of a plus h minus f of a minus L of h divided by h. Right? Because linear maps from R to R are precisely given by multiplication of real numbers. Right? Okay? Now, so this was happening from R to R in the beginning. Okay? Now, I'll just change this and I will say my definition now is in a stage where I can adapt to the higher situation. So now I'll say that f from Rn to Rm to Rn, maybe Rm to Rn. A be a point in Rm. I could have taken an open subset in A. Instead of whole of Rm, I could have even taken an open subset of Rm. Okay? But those are all not so difficult to generalize. But then we say f is differentiable at A if there is a R linear map L from Rn, Rm to Rn such that limit of f of A plus H plus F of A minus L of H divided by H. I can even take I will take the norm here. This norm is the norm of N, and this norm is the norm of M as H go to 0. You see, I am just copying this definition. This is how I generalize the definition. One easy fact is the following, that is the exercise that every mathematics student should check. If this is differentiable, then this linear map is unique. That means if there are two maps, L1 and L2, then L1 is equal to this linear map. L is unique if it exists. Okay? That is not difficult to check. All that you need to check is, suppose I have a linear map from Rn to Rn, and suppose they agree on the unit sphere. Okay, Rn comes, there is a unit sphere in Rn, right? This is norm. Okay. So unit sphere contains all the directions. So if they agree, two linear maps agree on unit sphere, then they agree everywhere. Okay. Or for that matter, any sphere. If I take any sphere contains a basis of the vector space. If I take a sphere which is not a point around 0, it contains a basis of the vector space. That's easy to see. Okay. In fact, an orthogonal basis. So if two linear maps agree on a sphere, then they agree everywhere. And this exercise, the way I'll do, I need this fact, and it's immediate. If I take two L1 and L2, the difference, they will both satisfy this object, and you take the difference, and you will say that you're dividing H by norm H, which lies, if H is not 0, it lies in unit sphere. That becomes 0. Okay. So it is an easy exercise, it's a fun to do exercise, and you should do that. And then it will be clear that this linear map, it exists. This is called, it is unique. So now I am allowed, because of this exercise, I am allowed to call this L as the derivative of f at the point. Definition. Earlier my derivative was a number, but that number was nothing but a linear transformation. This is what I need. So derivative here now is a linear transformation. It is not a number. Okay? But linear transformations will be given by matrices. So earlier the derivative was a single 1 by 1 matrix. Now it will be going to be, if you choose an appropriate basis, it is going to be n by n. Okay? So this linear map L is called derivative of f at A, and denoted by, let's say, d of f. And since I am mentioning A, I should be also maybe A. All right, so this is the definition of a derivative. Now let's calculate. So derivative is a linear map, and linear map has a matrix representation. So linear map from vector space to another vector space has a matrix representation once you fix a basis of the domain and the range, right? So let us calculate, let us find out the derivative. Find out the matrix representation of dA with respect to the standard basis. Rn to Rm, I have a linear map, and Rn has a standard basis, Rm has a standard basis. So I'm going to find out the matrix of this linear map with respect to standard basis. So let us find out. So I would like to know what this dA of EI is. And what is EI? EI is 0, 1, 0 at the ith place. This is an element in R. Let's see what M. Right? So let us see what DI is. So I know, what do we know? The limit of h tends to 0, f of a plus h minus f of a minus d of f a of h. Suppose the derivative exists. All right. Now let us take TEI. Okay. And just plug in here. So plug in here. So what is this? It tells me the limit of t tends to 0, and t of ei is becoming this. So f of a plus TEI minus f of a minus d of f ei. This t comes here, and let's take t to be positive. I mean, when the limit exists, it doesn't matter from which way you are approaching. Let's take t greater than 0. And then it is becoming, norm of ei is, this is becoming 0, right? So this is, you will see that this is equal, and this is, so this is equivalent to saying d of, I cancel a lot of t's and so on, so d of ei is basically a limit of 0. Okay. So what is this? This is precisely the partial derivative of the function at a with respect to the variable xi, right? So this is simply d of f of xi at the point a. But f is f is simply, so f is f1 e1 plus it depends on Rn. So Fn, right? So then this becomes this becomes d of f 1 d of xi a e1 plus d of f n d of xi. Okay. So the ith column, so the ith, if I take the matrix representation of this linear map D of f at A, when I evaluate at the ith vector, what I get? I get the ith column, right? That's how the thing goes, right? Yes. So the ith column of DAF the matrix DFA is simply D of F1 dxi, D of F dxi. Right? So what is it? This becomes an n cross m matrix. Right? So I have just now calculated the matrix of D of F with respect to the standard basis, and I am getting a matrix which is of the form, if you write D of Fi, Fj, D of Xi. In short, if you write, it's going to be like this. The n cross m matrix. This is called the Jacobian matrix of A. So this is an n by n matrix, and this is precisely the matrix representation of the derivative of F. Okay. All right. So now, this is going to be important. So let me just state a very important basic theorem in Rn to Rn calculus, which is called the inverse function theorem. So I don't know whether it is taught in BSc course or not. Is it taught? No. But this is an extremely important theorem, and is the first step in if you want to study differentiable manifold. So is this clear so far? If it's not clear, please stop me and ask questions. So the inverse function theorem. Abhishek, এখন আর কতক্ষণ মানে
তাহলে আর 10 মিনিট হলো 5 মিনিট
আর 4 মিনিট বলেছো তারপর আবার ঠিক আছে Okay, so what is an inverse function? What is inverse statement of the inverse function theorem? This proof is, I mean, there are many books, basic books. You can look at the proof, but this is knowing the statement is very important. So let me just state the statement. So F is a map from Rn to Rn. This time both domain and range have the same end. F is C infinity. What is the meaning of a C infinity function from Rn to Rn? That means if the component, so F is given by n functions, right? F is given by n functions. The image is F is like f of x1 to xn is like f1 of x1 to xn and so on, right? Fn x1 to xn. Right? This is how it is. Rn to Rn function. So this is called a C infinity function if all the partial derivatives of all order, if they exist and continuous. Okay? This is called a C infinity function. So F is assumed to be C infinity here. And suppose A is a point in Rn. So it's a fact. It's a fact that if F is C infinity, then F is differentiable. Okay. I have defined C infinity in terms of partial derivatives, but I have defined differentiability in terms of some linear transformations and so on. But if F is C infinity, then it is differentiable. So I can talk about, so F is differentiable in particular since it is C infinity. And suppose A is in Rn, and suppose this important condition that T of F of A is non-singular. That is, It is a linear transformation which is bijective. That is d of, recall that d of f of A is a linear map from Rn to Rn. Is a linear map. And suppose this is bijection. So non-singular means it is bijection. In other words, the matrix representation, any matrix representation is inverted. Then there exists an open set U of Rn, U containing A, such that the conclusion is f of U is open. Okay. Secondly, f from U to f of U is bijective. And f inverse from f of U to U is single. Okay, or maybe I should write differentiable. So if I manage to see that at A the matrix is non-singular or the linear map is bijective, then there is an open set around. So let me draw some picture so that will be clear. So I have a map from, let's pretend that I am in Rn, although I am drawing a picture of R2. Yeah. And suppose, so let's take, suppose my point A is here, and I have a map from F here. Yes. So suppose at the point A, the map DFA is non-singular, then that means there is an open set around A. Let's call it U, such that f of U, this is f of U, containing f of A, that's also open. And f restricted to U is a bijective map from F to f of U. And the inverse map from, so once I have a bijection, I can talk about the inverse, right? The inverse map from f of U to U is also differentiable. So that's the statement of inverse mapping theorem. Okay, it's an extremely important theorem which says, which is going to be very useful. Okay? So but let's take f from R to R. Take f x to be x cube. Okay. Then you will see that d of f is a C-infinity function. D of f of 0 is 0 map. Is a 0 map. So it is highly non-zero. Okay. Around 0 you cannot have. So the inverse is going to be 1 by x to the power 1 by 3. That is not going to be seen. But if you remove the point 0 everywhere, it is seen. Okay. So this gives an example of the theorem. Okay. That. So in fact, this non-singularity is also equivalent that this f inverse exists. This is equivalent. If there is an inverse in an open set, then this matrix is going to be non-singular because of because of the following fact. So this you can take this as an exercise. This is also an easy routine exercise. If I have map from Rm to Rn to, so let's say, RL, if you have map FG, suppose F is infinity, G is infinity, and A is a point here in Rm, and F is C infinity, G is C infinity, then derivative exists, and D of F compose G, this is going to be at A is going to be D of at G, it should be G compose. At F of A is going to be D of A. So D of G compose F is also a linear map. This time it's D of G. So I have this Rm, Rn, RL. So D of G compose F at A is a linear map, and this is a linear. This is a linear map D of A. This is a linear map D of G at A. The composition law says the derivative of the composite map is the composition of the derivative. Using that, if at all there is an inverse, that will ensure that this is a non-singular. Okay. So non-singularity is a consequence. It implies existence of inverse, and existence of inverse implies non-singularity. The other side is easy because just simply because of this. Okay, probably I'll stop now and continue in the next session.
আমরা আবার 3টের সময় এখানে জড়ো হচ্ছি, ঠিক আছে? 3টের সময় 3টা আড়াইটা বাজে। ওটাই কথা ছিল। তোমরা কাইন্ডলি একটু ওয়েট করো, you will have tiffin from us. Okay. এখন বল সবাই তো ম্যাথমেটিক্স নেই, সায়েন্স এর আছে, যারা আছে তাদের তারা বুঝতে পারে। ইন্টারেস্টেড ছিল আজকে তো একজন আছে আইপ্যাডে ও চার্জ দিতে হবে অনেক আছে। আমারই ছাপতে হবে, আমারই ছাপতে হবে।
মাঝে কাউন্টেবিলিটি জায়গাটা মিস করে দিচ্ছি। আমি ভাবলাম কেন কাউন্টেবিলিটি স্টাইল কথা এলো না। এসে আমি একটা জায়গা দেখেছিলাম যেমন কাউন্টেবিলিটি স্টাইল নেট স্পেস সেই স্পেসটা ইকুয়াল সেপারেবল স্পেস। আমি কি করেছিলাম তখন কথাটা আমি সঠিকভাবে জানি না। সেপারেবল ইকুয়াল অনলি ইফ ইপসিলন প্রেজেন্ট জিরো দ্যাট ইজ দ্য কাউন্টেবিলিটি স্টাইল। এখান থেকে বলি কাউন্টেবিলিটি ভুল করতে পারি না, আরবিট্রারি থেকে আমার কাউন্ট আসছে এতদিন ফাইনাইট আসবে, কাউন্ট এক্সট্রা আমি কেন করে দিচ্ছি? তো আমি একটা দেখেছিলাম জানি না আমি এটা করেছিলাম, তারপর আমি একটা টিচারকে পাঠিয়েছিলাম হচ্ছে অ্যাপ্লাইডে, খুব একটা সাহায্য করতে পারেনি। বিশ্বাস আছে অ্যাপ্লাইডে ছিল, আমি যথেষ্ট ভালো করতে আমি
আমি চেক করবো, চেক করা
ঠিক করেছি কিনা
অভিষেককে
সে তখন গ্র্যাজুয়েশনের টাইমে
মানে কি করেছে? এটা তো মানে এটা এই এক্সারসাইজটা প্রথমে করতে হবে। আমি যেটা বললাম কাউন্টেবল ম্যাট্রিক্স ফিগার এই জন্য আমি মিস চেক করা ফেক করা বিরাট চেক করা ইলেকট্রনিক ম্যাজিক ঠিকঠাক হচ্ছে বোঝা যাচ্ছে হ্যাঁ পিওর করেছো
আমাদেরকে নাম সিলেকশন তো মানে একটা দিন থাকতো না সদস্যের আমাদের
আসেনি हाँ सारा सुजीव
Okay. Okay, so now we are in a position to define what a manifold is. So, as I said, so topological spaces, so we have seen that we can talk of continuous function and differentiable functions over Rn and so on, Rn to R. Topological spaces are spaces where you can talk of continuous functions from space to real world continuous functions. And manifolds are going to be spaces on which you can talk of differentiable functions, and manifolds are spaces where you can do over which you can do calculus. That the kind of calculus that you do over Rn, you can do the similar kind of thing on differentiable manifolds. So differentiable manifolds are spaces which are locally like a Euclidean space. So let me just define formally. So let me just spend some time over it. It is not allowing me to write this.
সমস্যা না আসছে না হ্যালো হ্যালো আচ্ছা এটা মুছে কি করে আর এটা ঠিক করা যায় কি ঠিক করা যায় ঠিক করা যায় ঠিক ঠিক করা যাবে এরকমই চলবে নাকি রাজপন্ডি বিরাট মোটামুটি বিরাট মোটামুটি গুগল করলে ইয়ে হবে ডিলিট হবে ঠিক আছে তুমি একটু বড় বড় করে লেখো না বুঝল মানে বড় বড় করে লেখো ওকে okay so let's get back to this okay red দিলে আর খারাপ হবে ব্ল্যাকটাই বেটার একই আছে ব্ল্যাকটাই বেটার এইটা এখানে দিলে এটা মুছে এই দিকে বন্ধ করো আটা দাও ঠিক আছে ঠিক আছে ঠিক আছে ঠিক আছে okay okay so basically I want like to define differential manifold so let x be a second countable topological space which is housed off okay a chart so let's define a chart u phi is a pair where u is an open set and phi from u okay phi u inside Rn is an open set in X. Phi u is an open set
in Rn such that phi from U to phi U is a homeomorphism. Homeomorphism means it's a continuous map from U to phi U, and the inverse is also continuous. By the way, if I have, I'm just going to say, if I have a topological, if there are two topological spaces X and Y, a map from X to Y is said to be a continuous map if inverse image of open sets are open sets. Okay, that's the definition. Okay. All right, so it's like I have a set X and I have this U and I have this map. This is a phi U. This is inside some Rn. Phi from U to phi U is a homeomorphism. Okay, that's what a chart is. Okay, this n is some R. This Rn is some usual Rn under the usual topology. Okay. So now how do I turn the page, Abhishek? Huh? Like this. Okay. So now, suppose U, phi, and V psi are two. Let's call it. Let's just to say that I am emphasizing this n. Let's call it n chart. Okay. So are two n charts. They are said to be compatible if. So I have this. If so, let me draw a picture before I say what I want to say. So I have this X, I have this U, I have this V. Okay, this is U, this is V, this is phi U, this is phi V. So I have this intersection. If U and V intersects, I have this intersection, and I have this intersection under this map psi, phi, and I have this intersection going under this map psi. So I have a map. So suppose these are n charts. I will say that these charts are compatible if either U intersection V is empty set, that this U and V does not intersect. U here, V here, they don't intersect. Or if U intersection V is not empty, then this map phi inverse from phi inverse psi, compose psi, from this phi of U intersection V to. So this map psi inverse is taking this, and this composition map takes this to this. Okay, to psi of U intersection V is C infinity. Now you see that this is an open set inside Rn, and this is an open set inside Rn. This is because this phi is a homeomorphism from U, and similarly psi is an homeomorphism from V to an open set psi V in Rn, and similarly phi is a homeomorphism from U to an open set phi U of Rn. Now, since it is a homeomorphism, any open set goes. So, if I have homeomorphism between two spaces, homeomorphism is two topological spaces is a bijective bicontinuous map. It's a bijective map. It's continuous and its inverse image is also continuous. So it has the property that a set is open, a map is homeomorphism if and only for any open set its bijection, and if and only for any open set the image is also open set. So U intersection V is an open subset of this topological space X. So phi of U intersection V is an open subset of Rn because phi from U to phi of U is a homeomorphism. Similarly, psi of U intersection V is an open subset of Rn. And I have a genuine map from an open subset of Rn to open subset of Rn. Now I know what it means to say a map to be C infinity, because I know I have a map from Rn, an open subset of Rn to an open subset of Rn. We all know what is the meaning of the fact saying that this map is C infinity. That means all the partial derivatives of all order exist and they are continuous. So this relation is an equivalence relation on the space of charts. Okay, this compatibility. Either the domains they don't intersect, or if they intersect, then this thing happens. Okay. Now I am in a position to define differential manifolds. So a differential manifold M is a second countable Hausdorff topological space such that it can be covered by domains of charts compatible to each other, such that there is a collection of pairwise compatible charts, say U lambda, psi lambda, lambda is some indexing set, such that union of U lambda, lambda here is M. Okay. That means I have this topological space. I am covering by charts like this, so that any two charts, whenever they intersect, the transition function, this is called transition function. Okay, this is called transition function. The transition functions are C infinity. Okay, so this is called differential manifolds. Okay, so I should have a collection of compatible charts for which the domain of the charts cover up the entire manifold. Okay. So let me now just give some examples. This definition might look very abstract, but let me give some concrete examples. Abhishek, এই পাতাটা একটু পাতাটা হচ্ছে না, এটা প্লাস করতে হবে। অনেকবার করতে হবে। আচ্ছা ঠিক আছে, এটা আমি করব next time. Okay, so let me just straight away prove from scratch that the unit sphere, let's take S2, let's take x, y, z inside R3, x square plus y square plus z square equal to 1. Let me prove that this is a differential manifold. By the way, this n, for which this n charts, so collection of pair is comparable n charts. This n is called the dimension of the manifold, and written like this. Okay, it's called the dimension of the differential manifold. So I'm going to prove now from the very definition that S2, the usual unit sphere that we know, it's a two-dimensional differential manifold. Okay. So let me draw a picture of S2 in R3. So first of all, under the subspace topology of R3, this is a Hausdorff space and it is second countable space. So first two conditions are immediately satisfied. Okay. I have to just give you a collection of compatible charts for which the domain, the union of the domain of this chart cover up entire S2. So let's take U1 plus to be x, y, z in S2 such that z is greater than 0. That means the upper hemisphere. And let's take U1 minus, or maybe let's call it U3. X, y, z in S2 such that z is less than 0. And let me just give a map. So I have a cap here, right? I have a cap here. I just press the cap to the two-dimensional plane, xy plane. Okay? So I have this cap here. Right? This is a cap. And what I give, the surface of the sphere, upper hemisphere, I just project it down to this xy plane. So what is the map? From U3 plus, let's call it phi 3 plus, to R2, phi of phi 3 plus of xyz is simply xy. Right? It's a bijective map from the upper hemisphere to the disk. I'm just flattening. Okay, I'm just pressing and flattening. It's a bijective map. Similarly, I consider minus from the lower hemisphere. I have this lower hemisphere. And I also again push it up. So similarly, U3 minus to R2, phi 3 minus xyz as again xy. I'm pressing it up. I can do this. So I have gotten two charts like this. I'm going to get 6 charts. What I'm going to do is the following. I have this unit sphere, and I have then this side, right? This side is x, y, z, so that x is greater than 0. And similarly, I have domain of the chart x, y, z such that x is less than 0. So these are all going to give me charts. And I'm going to press it to YZ plane. Okay, I have this chart. I'm going to press it to YZ plane. Similarly, I have this chart. I'm going to place it to yz. Then I have the y-axis, right? This is x-axis, this is y-axis, this is z-axis. Then I have x, y, z such that y is greater than 0 and x, y, z, y less than 0. I have this front part and the back part of the sphere. I press it to the zx plane, and from front and from back again I press it to the zx plane. Okay, so I have altogether 6 chart, and a domain of 6 chart. You can see that every point is covered. The union of, so if I take any sphere, okay, one of the coordinate must be non-zero, right? X, y, z. If I take x square plus y square plus z square is equal to 1, that ensures that one of the x, y, z must be non-zero. So one of the x, y, z. So let's suppose z is not 0. Then z must be either positive or negative. So the union of these charts fill up by the same logic. If z is not 0, z plus, so z positive, z has to be either positive or negative. Then z belongs to that first set of 2 charts. And if y is not 0, then y is either going to be positive or negative. Similarly, if x is not 0, x is going to be either. So these 6 charts basically cover, domain of the 6 chart cover up the entire sphere. And it is an easy case by case exercise that the transition functions are going to be, so you can see that if I have another thing here, okay, so another, so suppose I consider this and this chart, so this upward and this chart, then the part that is intersecting is this part, and if you can calculate the transition functions, you'll end up getting a C infinity functions from an open subset of R2 to an open subset of R2. So this is an exercise for you to check do the final checking that this gives me a 2-dimensional manifold. Okay. Similarly, so for example, if I take the paraboloid, so if I take the, let's take the paraboloid. So sometime, so if I take the paraboloid, what is the equation of the paraboloid? So it is z is x square plus y square, right? Right? This is the paraboloid. Okay? And this I can, so this paraboloid is also a 2-dimensional manifold. I can simply, so P is x, y, z such that this. So from P, I can do it with a single chart now, R2. I can simply send x, y, z to x, y. This is going to give me a single chart. So in case of paraboloid, it's a 2-dimensional manifold, but I can cover it, I can do it a single chart because this entire single chart is going to do the job. Okay. But it's not always true because of some deep reasons you cannot get a single chart for S2. Okay. From topological. Okay. So these are examples of manifolds, but actually we have given examples of something called a submanifold. Okay. So what is a submanifold of a manifold? So we have seen the manifold has compatible charts. So suppose M is a manifold. And N is a subset. Okay. So suppose the dimension of M is M So let me draw a picture. Suppose this is M, and suppose this is N. N is called a submanifold. N is called a submanifold if for all point alpha in N, let's call it alpha, I can get a chart. There is a compatible chart U phi compatible to the manifold chart, compatible to the charts of the manifold. So manifold means I have a compatible collection of charts. So this chart should be compatible to those charts such that U intersection N, that means U intersection N, that is this part, phi of U intersection N is phi of U intersection Rn cross 0. Okay? Submanifold of dimension, submanifold of, let's say, called N submanifold. N is subset, and suppose N is less than equal to dimension of M. Then this N is called N submanifold if there is a chart for every point P, there is a chart such that alpha here, alpha is in U, and phi of U intersection N, that is phi of U intersection N is this part. That goes to Rn, this is my R2, right? This part. This is suppose phi U intersection Rn cross 0. I'm drawing a picture of R2 and giving you an example of a manifold of dimension 1. In this picture, N is a manifold of dimension, N is a one submanifold. So that's why I have drawn a picture in R2 and shown you that this R cross 0. So this line is R cross 0. So in general, if M is a manifold of dimension N and N is a subset, then N is called an N submanifold if for all point alpha in N there is a compatible chart so that phi of U intersection N, that means this part, this is my U intersection N is taken to R phi of U intersection Rn cross 0. Okay. Now, I mean, just from the definition, and one can easily show that this for, so I demand that for every point alpha in N, I will get a chart like this. So if I vary alpha in N, then I get a chart whose union covers up the entire N. So I take N intersection those charts and I restrict my phi to those U intersection N, then I get an homeomorphism from U intersection N to Rn. Okay. So the point is, this definition, from this definition, it is kind of routine check to show. So let me just quickly give this, and this is an exercise that show, just from the definition, show that if N is a N submanifold, then the above these charts, this type of charts, then these charts give us a chart Compatible gives us a compatible. There's some work to do, but I'm just pushing it under the rug because there is a work to do, but this work is routine work. That means once you start, you'll finish. You don't have to think much. Okay. So something like I have to go to, let's say, Bardhaman. I know it's easy. I take just bus and go. I don't have to think. Okay. So it's something like that. So it is a work, but it's an easy work. So show that N is a submanifold, then this chart gives us a compatible chart for N, so that N is a differential manifold of dimension N. So a N submanifold is actually a differential manifold. Okay. So we have given examples of spheres, paraboloid, etc. Hyperplane. These are all hyperplane in a 3 space. These are all submanifold of dimension 2. Okay. So submanifolds are manifolds. Okay. So let me give you an example. So proving something, the subset is a submanifold is a very cumbersome job sometimes. You have to run through this entire process of giving charts and so on. But there is a much easier way to do when I'm giving you a baby example, but there are much easier way to construct submanifold which will arise as level sets of functions. Okay, so let me just say what exactly things are. So f is a function from Rn to R. Suppose this is a C infinity function, and I'm going to show you the power of inverse function theorem now. And let's choose a point C in R such that F inverse C is a non-empty set. For example, if I take R n to be 3, then I can have the function f of x, y, z is equal to x square plus y square plus z square. Then my unit sphere is f inverse 1, right? My unit sphere is just f inverse 1. So suppose that for all alpha in f inverse C, this vector d of f of x1 at alpha, d of f of xn at alpha is not a zero vector. Suppose I have the C such that f inverse C is non-empty, and for all alpha in that level set, this condition is satisfied. This is an important condition. Okay. So sometime when this condition is satisfied, there is a different name for it. This is called F is a submersion. Okay. So it's just a name, but if you translate that name into actual mathematical terms, this amounts to saying that this vector is not zero. One of this is the same as saying as one of the partial derivative at alpha is not zero. Okay. Then F inverse C is a submanifold, is a n-1 submanifold. Okay, so this in particular says that F inverse C is a differentiable manifold of dimension n-1. And to see a quick proof, it's kind of a very nice proof. So just for simplicity, let us assume that d of dxn at alpha is not zero. You can do it with anything, but for simplicity, let us assume that. So what I'm going to do is I'm going to give a compatible chart around. So I fix a point alpha in F inverse C, and I'm going to give a compatible chart of Rn so that F inverse C intersection Rn goes to Rn minus 1 cross 0. Okay, so that's what we are going to do. Okay, so now let us assume for simplicity that the last thing is not 0. So now define a map from Rn to Rn. How do I define? I define a map xn to x1 to xn minus 1, and then take, and it will be clear why I am doing like this. My aim is to prove that this function this capital F satisfies at alpha satisfies the condition for inverse function theorem. That means that alpha, the Jacobian of F is a non-singular matrix. And why is it like that? So if I can calculate the Jacobian of F at alpha, this is going to be something, if you just write down, this is exactly why I have chosen dfxn alpha not equal to 0. You can do it with the other coordinate. If dfx psi not equal to 0, then the xith coordinate should be replaced by f. Okay, so that's all it matters. So here it will be 1, 1, 1, 1, 1, and the last coordinate it will be d by dxn. And there should be something here. So the whole point is the determinant of this d of f of alpha is simply d of f by dxn at alpha. This is going to be this, and this is not 0. So there is an open set of Rn, so that f of capital F of that open set is also open, and that is going to be a chart. Okay. So there is an open set U such that f of U is open in Rn, and f from U to f of U is a bijection, and f so that f inverse from f of U to U is also differentiable. Okay. Now, by the very construction, if I look at this function f of U, then you see that let me take f of c minus c. F of the function I take f of x1 to xn, the last coordinate it goes to f of x1 to xn minus c. And it will be clear why I am doing like this. Now, something which satisfies f of x is equal to c should be having the last coordinate 0, right? So if I consider f inverse c intersection U and I apply f, then it is going to go to f of U intersection Rn minus 1 cross 0. And something which has the last coordinate 0 has to belong to f inverse c. That is by very definition. Okay. So I have just given you a compatible chart around alpha, and you can do it for every point. Okay, because of the condition, because of this condition, because of this condition. So this has a remarkable effect. So this shows the power of inverse function theorem. So this has a remarkable effect for proving that the unit sphere f of. So now take f of. Let's reprove the fact that this is a two-dimensional manifold. So f of I take x, y, z to be x square plus y square plus z square. Now I consider f inverse 1. So at f, if I alpha belongs to f inverse 1, then what is d of f of dx, d of f of dy, d of f of dz? That is 2x, y, z, right? Now, if I take alpha, this is alpha, this is alpha, this is just 2 times alpha. This vector is just 2 times alpha, right? At alpha. Alpha is a point in F inverse C. Now this cannot be 0 because alpha cannot be 0. Alpha is in unit sphere. This vector cannot be 0 because norm of alpha is 1. Alpha, if alpha is alpha 1, alpha 2, alpha 3, this is going to be 2 alpha 1, alpha 2, alpha 3, and which is 2 alpha, which is the vector 2 alpha. So 2 alpha can't be 0 if alpha is in F inverse 1. So it says at one stroke it says that this is a submanifold of dimension 2. It's a 2 submanifold. So S2 is a 2-dimensional submanifold. So it is a 2-dimensional example of a 2-dimensional manifold. You can do the same thing for the paraboloid. So this inverse function theorem gives us a way to cook up examples to prove that some level sets are submanifold. This is a very important result. So now, okay, so I have defined differential manifold. I gave examples of submanifolds. Now, if I take 2 differential manifold, M and N, suppose M is a differential manifold and N is another differential manifold, then I take the cross product X, X and Y, Y. That is also a differential manifold. And why? Because if I have a chart U psi for M, and if I have a chart V psi for N, then U cross V to Rm cross Rn. Suppose M is the dimension of M, N is the dimension of N, then psi cross phi from U cross V to Rm cross Rn, which can be identified with Rm plus N. This gives me, if I have a compatible chart for U psi and you have a compatible collection of chart for V psi, you take such products. So U cross V phi cross psi gives me chart for the product. So I give a product topology here. Product topology is the base for the product topology is open set cross open set here, and if it's so product of 2 Hausdorff space is Hausdorff, product of 2 second countable space is second countable. So all these conditions are easily satisfied. And now I have to give you a compatible chart. You have compatible chart here, compatible chart here. Just take that cross product like this, and you have to just check that this is a compatible chart. So that is also an easy routine checking. It is a straightforward checking. I leave it to you to check. And so product of 2 manifolds are also manifolds. Okay, so the whole point is product of 2 manifold is a manifold where the dimension adds up. If M is M dimensional manifold, N is N dimensional manifold, then M cross N is M plus N dimensional manifold. Okay. Now I have defined product. So the definition of Lie group is almost within our reach, because now G is a differential manifold and G is a group. Okay. So from G cross G, okay, I have to define what a smooth map is. So okay, so I should define what a smooth map is. So M is a manifold, N is a manifold, and I have a function f. So okay, so F is called a smooth map if for all alpha in M there is a compatible chart, there are compatible charts. So basically the whole game I am playing locally. Okay, every time I am defining something, I am doing locally so that I can just copy what we do for Rm to Rn, such that alpha is in U, V psi of M of N, such that if alpha is in V and such that f of U is inside V, and psi so phi inverse F compose psi from U from phi of U to psi of V is C infinity. So let me draw a picture here. Here I have two manifolds. I have this map there, and I have this point alpha. I am demanding that there is a chart here, and there is another chart here of F alpha. So that this U, this is V, this is phi, this is psi, and I'm demanding, this is a part of the condition that f of U is inside V. Then this makes sense, and this is in Rn, Rm, this is in Rm, and we all know what it means to say when a map from Rm to Rn is C. Okay, so this says that if it happens for all alpha, then I call this map as a smooth map. Now, there is a point I should mention that in calculus, we many times we prove that a C infinity map, a differentiable map is continuous. But here there is the subtle point is either you begin by assuming the map is continuous, or you assume this condition that if U inside V. If you assume the map to be continuous right at the outset, then this condition is automatically satisfied. Okay. Or you don't assume map to be continuous, then assume this condition, then that will prove that the map is continuous. So in case of manifolds, there is a bit of a jugglery goes on to prove the smoothness or differentiability of a map. You first assume the map is continuous, then give this condition. Then this condition is automatic, and then just end up giving this condition only. But if you don't assume if you don't assume continuity, then you have to assume this map. This is so a map to start with will not satisfy this condition. Okay, so that's the drawback here, but that is how it is. So one has to go like this. So yeah, so now I have this group G. I have this, and G is a manifold. G cross G to G, I have this XY map. And G cross G is a manifold again by whatever I said. So it makes sense to say when this map is smooth, and from G to G, X going to X inverse is also smooth. So this says when a Lie group, so what is a Lie group? So we understand, I have defined all the terminologies in order to define a Lie group. So G is a manifold, so G cross G gets a manifold structure because a product of two manifolds is a manifold, and G is a manifold, and I have an additional map given from G cross G to G since it is a group, X comma Y going to XY. I demand for it to be a Lie group that this map be smooth and the inversion map is smooth. So this is what Lie group is. Now, as I said, you can check that from R to R is a Lie group, Rn is a Lie group, and GLNR is a Lie group because matrix multiplication. So GLNR is an open subset of Rn, Mn square. Sorry, Mn is same as Rn square. So GLNR is an open subset of Rn square. Okay, so open subset of a manifold is a manifold. So I'm getting a manifold structure on GLNR as it is an open subset of Rn square. And the multiplication is given by C infinity function. Okay, if I take variable matrix variables, then if I take two matrix XY, their multiplication is just polynomials in the matrix entries. So it is of course a C infinity function. And the inversion is also can be expressed in terms of not polynomials but certain functions which are inverse of non-zero polynomials. There is a determinant will come below, right? I have a formula for computing inverse, if you recall, right? We know how to compute inverse of a matrix by a specific formula, right? I take every entry, take the corresponding remove that column and row, take adjoint of this, form the adjugate. What is it called? Adjugate. Then I divide the appropriate power of determinant, and that gives me a formula for determinant. All this process gives me a C infinity function. Okay, so that is why GLNR is an example of a Lie group. Now the point is there's a very deep theorem in Lie group. I am towards the very end. I'll just say a couple of words more and then stop my lecture. So how to produce Lie groups? So Lie groups. So there is a theorem in Lie group theory. If you look at the theory of Lie group, there is a very deep theorem that comes in the very beginning that a closed subgroup of a Lie group is a Lie group. Okay, it's a very deep theorem. Closed subset of a manifold need not be a manifold. Okay, but if I have a Lie group, then if I have a closed subgroup, okay, a subgroup which is a closed subset, then it gets a submanifold structure. It's a very, very strong result. Okay, so this result gives a huge number of examples of Lie groups, Lie subgroups of GLNR. For example, I have seen matrix group which is called SON, the orthogonal matrices. This is a closed subgroup of GLNR. Similarly, I have symplectic, all kind of matrix SLNR. SLNR is a closed subgroup because it is determinant. SLNR is the matrices for which determinant is 1. So that's a closed subgroup because it's a determinant is a continuous function. It is inverse image of 1. That is a closed condition. So this is a closed subgroup. So these are examples of Lie groups. Okay, and but so these are Lie group examples of Lie subgroups of GLNR. But it is another fact that all Lie groups cannot be thought as a Lie subgroup of GLNR. This is a so there are Lie subgroups which cannot be linearizable. That means you cannot get any GLNR. You cannot put inside any GLNR. There are examples like that. Okay, so GLNR is a rich source of. It gives a rich source of Lie groups. And you take any closed subgroup, it is going to be a Lie group. Okay, so I think I'll stop here. I wanted to say some more thing, but I think it's a good time to stop.
So let's give him a big round of applause. So
Oh, question, yeah. Any question?
আছে কিছু কোশ্চেন আছে?
না স্যার এটি
এটা বন্ধ করে দাও। বন্ধ করে দাও। বসো। স্যার আসুন। বসে দেখো। কোনো রেফারেন্স থাকলে তো বলতে হবে।
ও
রেফারেন্স আর লিখে দাও। রেফারেন্স লিখে দাও।
রেফারেন্স কোন ফলো করছেন?
This is a very nice article by Roger Howe. এটা ইন্টারনেট আছে না? হ্যাঁ হ্যাঁ। Very basic detail. কাল লিখা Roger Howe পাওয়া যায়। এটা কি ঝামেলা তো? আসছে না। Very basic. Roger. Very basic. Roger Howe. Basic. Click for Howe. No. So there is an article by Roger W. Called very basic theory. This article appeared in Mathematical Association of America. So this gives the first here. You can share, it is freely available now.
স্যার আপনারা কি বইতে লিখছেন?
Introduction to why e-book is important and some very famous theories. Roger Howe representation theory. Huh? Yeah. Now there is another nice book by Morin called Introduction to Differentiable. Not calculator. Introduction to Manifolds.
অনেকগুলো বই আছে।
So this is a very beautiful. Second lady. Share this picture also. So these are very basic books, and you can nowadays you have internet, so there is huge.
Introduction to Manifolds.
So you can have a look at this. This is a book which you will also able to understand. It doesn't take much. But several books. So he has written many books. So he has written a book on differential geometry. is slightly advanced book.
ডিফারেন্সিয়াল ফর্মস এর রয়েছে।
এইটা হচ্ছে, হ্যাঁ এটা খুব দারুণ বই একটা। এটা this book is very advanced book. So
আচ্ছা, একটু গ্রুপে বা কোথাও একটু লিখে দেবেন মানে।
হ্যাঁ, বলে দেওয়া হবে।
থ্যাংক ইউ স্যার।
so this is a book by differential geometry, connection curvature, but this book, this is a very advanced book. This is a book which is on principal bundles, so you don't have to like worry about it. The first book is very nice. And Loading 2 has another book on bot and tube, which is a very famous book by Raoul Bott and Loading 2 on algebraic differential forms in algebraic topology. And he has another book on another book. So this book is very nicely written, very basic. You can look at that book. And there are huge number of articles in the internet. First read this article. This is a very beautiful article. It gives you some glimpses of the good here. And there are series of advanced books which I don't want to say. So another very classic book is by Frank Warner.
লিখে নাও।
This is
আচ্ছা, তোমার আছে?
Differential Manifolds. This is slightly advanced book. The language is slightly more sophisticated. And there are series of books on Lie groups. So this gives the basic foundation of Lie groups, but there are more specialized books on Lie groups. So yeah, so first I think it's good to read these books, and then there are classic books by Helgason and Antonina. So there are huge number of books on this. This is a very important area. So you just search in the internet, you will get huge number of articles, huge number of expository articles, huge number of books. So all the informations are here. This is
বেসিক্স এর জন্য তো মোটামুটি প্রেসলির বইটা সব থেকে ভালো, বেসিকটা এই করার জন্য। আপনি অ্যাডভান্স গুলো বলছেন?
হ্যাঁ, ঠিক আছে।
হ্যাঁ,
আজকে আমরা এই ডিফারেন্সিয়াল ম্যানিফোল্ডস এবং লি অ্যালজেব্রা যে কানেকশন সেটা বললাম। এখানে অনেকটা টেকনিক্যাল টার্ম আছে, আমরা ফিজিক্সের লোক অতটা ভালোভাবে বুঝতে পারি না, কারণ হচ্ছে যে বেশিরভাগটাই আমাদের ট্যানজেনশিয়াল হয়, ট্যানজেন্ট স্পেসে যায়। এখন আমি একটা কথা বলি, সেটা হচ্ছে যে আইনস্টাইনকে 10 বছর মিচেল ব্রসম্যানের কাছে ম্যাথমেটিক্স শিখতে হয়েছে আলটিমেটলিটা, কিন্তু আমরা 10 বছর বাদে উনি ওই জেনারেল রিলেটিভিটি সুবিধা দিতে পেরেছেন রিমান স্পেসের সঙ্গে কানেক্ট করে। আমি আস্তে আস্তে বলছিলাম সেটা হচ্ছে যে রিমান স্পেসের যে ব্যাপ্তি এটা এখনো পর্যন্ত বুঝে ওঠা যায়নি আমার মনে হয়। তো খুব সুন্দর আমাদের
প্রফেসর প্রলয় চ্যাটার্জি বলেন, উনি অনেক দূর থেকে এসেছেন, চেন্নাই থেকে, এবং আমরা খুব লাকি ওনাকে পেয়েছি। এবং আমার একটা বড় প্রাপ্তি হচ্ছে যে আমি স্যারকে পাওয়া, আমাদের কৃতিশন চ্যাটার্জি স্যারকে আমরা ডিপার্টমেন্টে দেখেছি। আমার স্যারের ছবি মনে পড়ে, স্যার একটি সাইকেল নিয়ে আসতেন এবং যে কোনো প্রশ্নের উত্তর স্যার দিতেন, বললে সুন্দরভাবে ব্যাখ্যা করতেন। আমি একটা একাডেমিক স্টাফ কলেজে একটা প্রোগ্রামে অ্যাটেন্ড করেছিলাম। সেখানে ও যেমন বলছে যে অনেক পার্টিসিপেন্ট ছিল, বিভিন্ন ডিপার্টমেন্টের লোকজন ছিল। তা স্যার সেখানে একটা প্রেজেন্টেশন দিয়েছিলেন। প্রেজেন্টেশনটা স্যার একটা গল্পের মতো বলেছিলেন। গল্পটা হচ্ছে যে গোলবাগ কনজেকচার, আঙ্কেল পেট্রোল অ্যান্ড গোলবাগ কনজেকচার। এই গল্পটা স্যার ওখানে বলেছিলেন আমাদের, যে ওই একটা বই আছে কি বলছে বইটা। তা ওই বইটাতে স্যার গল্পটা বলেছিলেন যে একটা মানুষ তার সারা জীবন ধরে কিভাবে একটা প্রবলেমের পেছনে থাকতে পারে, এই গল্পটা স্যার আমাদের ওখানে বলেছিলেন। খুব ভালো লেগেছিল গল্পটা। তারপরে বইটা স্যারের কথা শুনে বইটা পরে কিনে আমি পড়ি। আপনারাও যদি বইটা পড়ে থাকবেন তাহলে ভালো লাগবে আমাদের। আমি সবচেয়ে ধন্যবাদ জানাই আমাদের কলেজের প্রিন্সিপাল স্যার তাপস সামন্তকে, আমাদের অনেক প্রেসিডেন্ট তাপস কাপ্পা মহাশয়কে, এবং আমি ডিপার্টমেন্টে ম্যাথমেটিক্স ডিপার্টমেন্টে আমরা অভিষেক, সুলতান যারা আছে তাদের সকলকে ধন্যবাদ জানাই। পর্যন্ত সুদীপ অনেক দূর থেকে এসেছে এই লেকচারটা অ্যাটেন্ড করতে। আমরা অভিষেককে ধন্যবাদ জানাচ্ছি বিশেষ করে, কারণ অভিষেক অনেক এফোর্ট নিয়েছে যে এই সমস্ত জিনিসগুলো টু এক্সপোজ টু স্টুডেন্ট, মানে স্টুডেন্টকে এক্সপোজার দেওয়ার জন্য। এবং ও একটা সামার স্কুল করেছিল, তখন আমি বলাই অ্যালজেব্রা এবং এটা শুনেছিলাম। এটা আমাদের ফিজিক্সের খুব কানেক্টেড, কারণ হচ্ছে আমরা পার্টিকুলার ফিজিক্সে এবং ডাইনামিক্সে এই তার অ্যাপ্লিকেশন ওয়াইড অ্যাপ্লিকেশন আছে আমাদের, বিশেষ করে ফাইভ মডেল ফিজিক্সের যেগুলো সুপারসিমেট্রিক গ্রুপ যেগুলো করে আর কি, সেইগুলোর ক্ষেত্রে এটা খুব একটা ওয়াইড অ্যাপ্লিকেশন আছে। আমরা অঙ্কটা অত বুঝতে পারি না, কিন্তু তার অ্যাপ্লিকেশন পার্টটা হচ্ছে বুঝতে পারি, অ্যাপ্লিকেশন পার্টটা বুঝতে পারি। আমার খুব ভালো লেগেছে ও এত সুন্দর করে এক্সাম্পল দিয়ে প্রলয়বাবু বলছিলেন, খুব সুন্দর লেগেছে আমার। এবং এটা লেমেনের পক্ষেও খুব ভালো, যারা খুব একদম এগিয়ে আসছে তাদের কাছেও ভালো। আমি আশা করবো যে উনি আমাদের কলেজে আবার আসবেন এবং আমরা ওনাকে আবার পাবো, এবং আমাদের আরো প্রাপ্তি হচ্ছে স্যারকে পাওয়া। স্যারকে পেয়ে আমি ধন্য। আমি বলেছি যে স্যার আপনি আমাদের কলেজে গেলে কলেজ ধন্য হবে, সত্যি ভাগ্যবান। সকলকে ধন্যবাদ জানাই এখানে আসার জন্য, ছাত্রছাত্রীদের ধন্যবাদ জানাই যারা অধীর আগ্রহে শুনেছ। এবং এটা মনে রাখবে যে ভালো জিনিস শোনা, ভালো জিনিস দেখা, ভালো বই পড়া এটা খুব দুর্লভ জিনিস। এটা যখন পাওয়া যায় তখন সেটা রাখতে হয়। সবাই ভালো থাকবে। খুব ভালো লেগেছে, আমার তো আমার দারুণ লেগেছে। আমি কিছুই জানি না প্রায়, কিন্তু